The core issue is gradient conflict, which is especially problematic due to the nature of heat map supervision. So what makes HamiPose estimation so tricky? Unlike classification, we're dealing with heat maps. Think about it. Both your source ground truth and the target pseudo-labels are these sharp, narrow peaks. A tiny localization error, maybe just a pixel off, can completely flip the direction of the gradient because the response surface is so steep around that peak. Now throw in the fact that pseudo-labels aren't perfect. They vary in quality depending on occlusion, blur, or truncation. This creates a heterogeneous mess. Some joints might be easy, others impossible. This combination of sparsity and heterogeneity amplifies the mismatch between simple Euclidean similarity and the underlying geometry of the problem, leading to those frustrating oscillations you see in optimization. It's like trying to steer a ship with a rudder that sometimes pushes forward and sometimes backward, depending on which joint you look at. To tackle this, we introduce HamiPose. Our core idea is to borrow concepts from physics, specifically Hamiltonian dynamics, to model the optimization process itself. Why? Because Hamiltonian systems are great at describing systems with oscillations and long-term evolution, and they have properties like conserved quantities and structure, preserving trajectories that help prevent artificial energy drift and numerical overshoot. We treat the loss landscape as a potential energy surface and introduce a data-driven metric that defines the kinetic energy. This allows us to transport parameter updates along paths that respect the geometry of the problem using controlled momentum. This framework provides a stable foundation for optimization under these challenging, sparse, and heterogeneous supervision conditions. First step, we need to understand the conflict better. Comparing raw gradients across different key points, like shoulders versus fingertips, is apples and oranges. They operate on different scales. So, for each key point k, we decompose the target gradient gt superscript k into two parts relative to the source gradient gs superscript k. We use a block diagonal metric dk superscript t-1 learned from past updates to normalize the geometry. This gives us a parallel component gt parallel superscript k, which is aligned with the source, and an orthogonal component gt perpendicular superscript k, which is perpendicular to the source direction in this normalized space. The beauty here is that the orthogonal part, by construction, doesn't interfere with the source's descent direction. It's essentially non-conflicting information we can safely pass through. Okay, we've isolated the non-conflicting orthogonal part. But what about the parallel part, GT parallel? Even after normalization, it might still be pointing in the wrong direction due to noisy pseudo-labels or occlusions. We don't want destructive interference, so we apply a gate phi k. This gate is smart. It first checks the alignment rho k. If it's not positive, the gate is 0, blocking that component. Then it uses a confidence score ck derived from the teacher's prediction peak strength. Higher confidence means we trust the alignment more. Crucially, we anneal the sensitivity gamma of t during training, starting lenient and becoming stricter as the model gets more reliable. Only the positively aligned, confident parallel components get through. We combine this filtered parallel part with the orthogonal part to form our process target gradient tilde GTPC, which we then add to the source gradient scaled by lambda. Even after filtering, the remaining signals are sparse and heterogeneous, potentially causing high-frequency jitters in the parameter updates. This is where the Hamiltonian optimizer comes in. We define a Hamiltonian H that includes the standard losses LCE plus a kinetic energy term involving momentum P and our adaptive metric D. The key is how we update theta and P. We use the canonical equations derived from H. The parameter update theta dot is proportional to the momentum p, scaled by the inverse metric. The momentum update p dot is driven by the negative gradient of the total loss. We implement this using a symplectic Euler scheme, specifically a kick-drift kick step. This involves computing the filtered gradient GH, applying half a momentum kick, updating theta using the momentum, and then applying the second momentum kick. This structure inherently preserves the geometric properties of the system and provides that crucial inertia to smooth out oscillations without adding extra computational cost beyond scaling the momentum blocks. Let's quickly touch on the experiments. We tested HamiPose on standard benchmarks. For human pose, we transferred from the synthetic Saranol dataset to the real-world human 3.6M and LSP datasets. For hand pose, we used the RHD synthetic dataset and adapted it to H3D and freehand real-world data. Evaluation is done using the standard PCK at 0.05 metric, measuring the percentage of keypoints predicted within 5% of the image size from the ground truth. We also break down performance by major body regions or specific hand joints like MCP, PIP, dip, and fingertips to get a finer-grained view of accuracy. The results speak for themselves. On both human and hand pose tasks, HamiPose consistently achieves state-of-the-art performance compared to a range of strong baselines, including other UDA methods and those focusing specifically on gradient dynamics. Look at the overall scores: 83.9% on LSP, 79.8% on human 3.6M for humans, 83.1% on H3D, 59.9% on freehand for hands. These aren't just marginal gains. The advantage is clear, especially on challenging fine-grained metrics like fingertips and distal interphalangeal joints for hands. This demonstrates HamiPose's effectiveness in handling the complexities of sparse and heterogeneous supervision. Numbers are good, but seeing is believing. Figure 2 shows qualitative results. Compare the green skeletons from HamiPose with the ground truth. Across various datasets, HamiPose predictions are visibly closer and more accurate than those from other methods like SFUDA, PGDA, or DLPose. The difference is quite noticeable. We also looked at in the wild hand pose data from WBH, a benchmark based on COCO images. As Figure 3 shows, HamiPose again produces results that are closer to the ground truth, suggesting better generalization to unseen, challenging real-world conditions compared to other domain generalization approaches like GCA and GASMUM. Beyond adapting to a single target domain, we also evaluated HamiPose's ability to generalize to unseen domains. We trained on one target, say Saranol to LSP, and then tested directly on human 3.6M, which was never seen during adaptation. The results in Table 2 are impressive. HamiPose achieves a solid 77.5% overall accuracy on human 3.6M. Similarly, adapting on RHD to H3D and testing on freehand, a much larger distribution gap, HamiPose still delivers the best results with 52.2% overall. This indicates that the learned representations and the stable optimization process fostered by HamiPose lead to robustness across different unseen real-world scenarios. To understand what makes HamiPose tick, we did an ablation study. We started with a basic mean teacher setup. Adding our unified metric, which combines a global mass with channel-specific normalization, already gave a nice boost, especially improving accuracy on harder parts like hips. Next, adding the channel-wise gated filtering pushed performance even higher, showing the value of selectively removing conflicting updates. Finally, incorporating the Hamiltonian transport mechanism reached the final top-tier performance figures we saw earlier, with continued improvements on difficult joints like hips and fingertips. This confirms that each component plays a distinct role: normalization, selective filtering, and stable transport. We also compared our key point-wise strategy against a simpler unified gating approach. Figure 4 shows the evolution of the gradient conflict ratio over training epochs. Both start high as expected. However, the key point-wise gating strategy suppresses conflicts significantly faster and reaches a lower, more stable level of around 6% conflict, whereas the unified gate lingers around 8 to 9%. This suggests that evaluating alignment individually for each key point, considering its specific geometry and context, is more effective at resolving localized conflicts caused by occlusions or noisy pseudo-labels, leading to smoother and faster agreement between domains. Finally, let's look at the impact of the Hamiltonian optimizer itself. Figure 5 compares its loss curve against standard SGD and ADAM under identical conditions. You can see the difference immediately. SGD exhibits strong early oscillations, reflecting the overshoot caused by the conflicting source and target signals. ADAM does a bit better, damping some oscillations, but it tends to hit noisy plateaus later on. In contrast, the Hamiltonian approach shows a remarkably smooth, monotonic descent throughout the entire training period. This confirms that coupling momentum to the adaptive geometry provides an effective inertial smoothing mechanism, naturally filtering out inconsistent gradient bursts without extra cost. We also performed a hyperparameter sweep focusing on the alignment sharpness gamma and the warm-up duration for the annealing schedule. As shown in Table 5, performance is sensitive to these choices. Too low a maximum sharpness gamma max underutilizes aligned updates, while too high a value increases conflict. A very short warm-up introduces noise too early, while an excessively long one slows down initial adaptation. The sweet spot seems to be a moderate gamma max combined with a relatively short warm-up ratio. Based on this analysis, we selected gamma min equals 0, gamma max equals 2, and a 10% warm-up for our final results. In summary, HamiPose reframes the UDA pose estimation challenge as a problem of ensuring optimization consistency despite sparse and heterogeneous supervision signals. By combining a unified data-driven metric, key point level conflict filtering through geometry decomposition and confidence gating, and Hamiltonian transport with symplectic integration, we achieve state-of-the-art results on established benchmarks and demonstrate strong performance